Welcome back to the course entitled Chemical Crystallography. In the previous lecture, we discussed about various forms of structure factor and derived the expression for structure factor in terms of electron density and have shown that how they are related by Fourier transformation. So, in this class, we are going to talk about the various relations of structure factor in terms of rho HKLs, and then we will try to come to the systematic absence conditions derived from the structure factor expression. So, in the previous lecture, we derived the expression for the structure factor F as the sum over j Fj e to the power I delta j, where Fj is the scattering factor of ith atom or element, and delta j is the phase associated with the atom Fj, and this delta j we have seen is equal to 2 pi Hx plus Ky plus Lz. So, this F in terms of FHKL can be written as sum over j Fj e to the power 2 pi I Hxj plus Kyj plus Lzj. Now, when you consider a crystal, what we have is we have one asymmetric unit containing some n number of atoms, and then that asymmetric unit is repeated in 3 dimension inside the lattice using the appropriate symmetry of the lattice. So, if I consider one object having some carbon atoms, some number of carbon atoms, and the symmetry generates 4 such atoms, we need to do this summation once over all the atoms and once over 4 asymmetric units. So, that means we are doing a double summation of these structure factors in terms of the scattering factor. So, this expression can be written as F HKL equal to sum over n Fn, once again sum over m e to the power 2 pi I Hx m comma n plus k y m comma n plus L into z m comma n, where this small n number of atoms in the asymmetric unit and m is the z value, that is number of symmetry equivalent positions in the unit cell. So, this value of m can be equal to 1 in case of P1, 2 in case of P1 bar, P1 bar. It can be 2 in case of P2, Pm, PC, etc. And as you know, the Z value depends on the lattice type and the symmetry associated. So, in short, one can write FHKL as equal to sum over n Fn EHKL, where this EHKL is called the special form of structure factor. So, this does the sum over all the symmetry equivalent positions. So, now if we start using this concept for very simple lattice like P1 bar and then slowly move to the cases of P21 and so on, we will see how this structure factor expression changes its value depending on the symmetry that is present. So, suppose for P1 bar system, what are the corresponding equivalent points that we have? The corresponding equivalent points are x, y, z and x bar, y bar, z bar. So, when we try to evaluate EHKL for a triclinic system, I need to do a sum on these two individual points. So, we can simply write it as exponential 2 pi I Hx plus Ky plus Lz plus exponential 2 pi I minus Hx minus Ky minus Lz. So, if we now break these exponential factors in cos and sine functions, you can write it as cos 2 pi Hx plus Ky plus Lz plus I sin 2 pi Hx plus Ky plus Lz plus for the second term cos 2 pi Hx plus Ky plus Lz minus I sin 2 pi Hx plus Ky plus Lz. So, now what we see is that these sine terms get cancelled and we end up getting a result of EHKL as 2 cos 2 pi Hx plus Ky plus Lz. So, then the structure factor expression for FHKL in case of triclinic gets reduced to 2 sum over n Fn cos 2 pi h x n plus k y n plus L z n, where n is the number or identity of different elements present in the asymmetric unit. So, one can simply calculate the structure factor for different H, K and L for triclinic system if you know what are the elements present in the system. So, now if I try to see if what happens in case of a symmetry 2-1 screw parallel to y. So, when you have 2-1 screw parallel to y, the equivalent points are x, y, z and x bar, y plus half, z bar, right. So, now what will happen? If I try to write the EHKL for these 2 points which are generated by 2-1 screw, I get e to the power 2 pi I h x plus k y plus L z plus e to the power 2 pi I minus h x plus k y plus k by 2 minus L z. So, now again I am trying to separate these exponential terms e to the power 2 pi I h x plus L z into e to the power 2 pi I k y plus e to the power minus 2 pi I h x plus L z into e to the power 2 pi I k y into e to the power 2 pi I k by 2. So, now when I try to simplify this expression, you see that we can take e to the power 2 pi I k y out as a common term. So, then we are left inside with e to the power 2 pi I h x plus L z plus e to the power minus 2 pi I h x plus L z into e to the power pi I k, because this 2 and that 2 gets cancelled. So, now for general set of reflections H K L, E H K L is not 0, but when we put a restriction on H K L, that is for special type of reflections where H is 0, K is not 0 and L is again 0, what happens to the expression for EHKL? This H and L are 0. So, then the first term is e to the power 0, which is equal to 1. So, we get e to the power 2 pi I k y 1 plus the second term here is also, if you put h and l equal to 0, then it is e to the power 0, it is again 1. So, it turns out to be e to the power pi I k. So, now when this k is odd, that is equal to 2n plus 1, this e to the power pi I k is equal to minus 1, which essentially means that E 0 k 0 is equal to 0 for k equal to 2n plus 1. And if k is equal to even number, that is say equal to 2n, then e to the power pi I k will be plus 1. So, E 0 k 0 will be equal to 2 times e to the power 2 pi I k, which is not 0. So, from this we can derive the expression for systematic absence condition for a 2-1 screw as 0 k 0 set of reflections with k equal to odd, that is equal to 2n plus 1, E 0 k 0 is equal to 0. It means that for the set of reflections 0 k 0, the reflection will be systematically absent in your diffraction data in case of 2-1 screw parallel to y axis. Therefore, in the same way, if we want to determine the systematic absence conditions for C glide perpendicular to y, we have the equivalent points as x, y, z and x, y bar, z plus half. These are the two equivalent points of C glide perpendicular to y. So, then your expression for E h k l will be equal to e to the power 2 pi I h x plus k y plus L z plus e to the power 2 pi I h x minus k y plus L z plus k by 2. So, now we again break it into parts, looking at the similar terms which are h x and L z e to the power 2 pi I h x plus L z into e to the power 2 pi I k y plus e to the power 2 pi I h x plus L z into e to the power minus 2 pi I k y into e to the power 2 pi I k by 2. So, now we have this first term common in both. So, we take it out. Then we are left with inside e to the power 2 pi I k y plus e to the power 2 pi I with a minus sign k y into e to the power 2 pi I k by 2, which turns out to be 2 pi I k. So, this is the expression for the special structure factor E h k l for all general reflections. When we consider a special set of reflections, that is h 0 l having k equal to 0, this E h 0 l set of reflections will have this special structure factor expression as e to the power 2 pi I h x plus L z into, when k is equal to 0, this first term e to the power 0 is 1, In the second term, the first part is once again 1 and we are left with e to the power pi I k. So, now if k is odd, e to the power pi I k is minus 1. Therefore, E h 0 L is equal to 0 for k equal to odd. That means, the systematic absence condition is that H 0 L set of reflections having, here I made a mistake, it should be L by 2. Please correct it in this, it should be L, it should be L here. H 0 L with L odd, this L equal to 2n plus 1 will be absent. So, here this is how you can derive the systematic absence conditions for different symmetry operations. So, if somebody asks you to derive the systematic absence conditions for P C A 2-1 kind of a space group, you have to do this mathematics once for C glide perpendicular to x, once for A glide perpendicular to y, and once for the 2-1 screw parallel to z. So, these 3 mathematical derivations will give you 3 different conditions for systematic absence for this particular space group. So, I am giving you the answers, but you need to work it out yourself. When it is C glide perpendicular to x, the reflections that get affected are zero k L set of reflections, where L equal to 2n plus 1 will be absent. A glide perpendicular to B, that is H 0 L set of reflections with H equal to 2n plus 1 will be absent, and for 2-1 screw parallel to Z, 0 0 L set of reflections with L equal to 2n plus 1 will be absent. So, I leave it to you for deriving these expressions. So, I conclude here in this class with this derivation, and we will continue in the next class. Thank you.